Hello everyone, this is Kevin. Today I'm going to be showing you how to use Desmos 3D to produce models that you can actually 3D print, such as this 3D interpretation of the involute of a circle, these ruled surfaces that follow the path of a sine wave around a central position, and even this shoe. And of course, up until now, all this time, I've been filming myself with an actual functional piece that's been sitting on top of my computer screen and holding my phone. Now there are a couple of different tools that we'll be using to get that 3D data off of Desmos and onto our 3D printer. First one is of course desmos.com/3D, otherwise we wouldn't be able to do anything. Second is actually a bookmarklet designed by someone for a college project, and that will be linked in the description. It's from a GitHub user named MintExists. Now, I don't actually know how JavaScript works, but I plugged it into ChatGPT and had it explain how each individual section of the script works, and it seems to be pretty safe. Now, I'd recommend, because GitHub can change over time, I'd recommend that you skim it over if you decide to use this tool. But what it essentially does is it grabs the 3D data straight from the Desmos viewport and then places it into your downloads folder. Next, we'll be using Meshmixer to clean up the broken mesh a little bit because it is a bit of a hacky process. After which I'll be slicing it with Cura and then printing it on my Creality CR10. Alright, let's jump right into it. The first episode is a basic workflow tutorial, so I'll be brief on the math. To start off, you can find any 2D implicit equation you think looks cool. This one in particular is the implicit equation for the involute of a circle, and I got it from A Treatise on Infinitesimal Calculus, Volume 2, by Bartholomew Price. It was published in 1865 and therefore freely available on Google Books. So I basically just take those characters and type them exactly as they are into Desmos. Alright, that looks nice. Now, one thing you'll notice is that that's a 2D equation, not a 3D equation, and we're trying to make a 3D equation here. So what I'll do is I'll stick a z in there. And the reason this works is because the majority of implicit equations are essentially just density equations across a two-dimensional field. So instead of putting it equal to 0, if we put it equal to z, then that gets us our density field. One thing you'll notice, though, that's immediately going to pose a problem is that gaping hole in the center of the graph. We know why that is, because you can't take the square root of a negative, so I'm just going to clamp that to positive values. With a maximum function. And if I remove the axes, you see what that did. It essentially just capped it with a plane. I think that looks nice. So next thing, it's a bit taller than I would prefer. Maybe I'll divide that by 2. There we go. That's looking nice. Now, one thing else you'll notice is that at the moment it's an infinitely thin plane. So a few things we will have to do with that is move this z to the end of the equation. Just subtract it out there. And then if we make this an inequality, you see that it fills down to the bottom. Now, a few things else we can do with this. I don't particularly fancy that sharp corner over there. And no matter how much you zoom out, there's always going to be a sharp corner in this graph. So we're going to have to start dealing with Boolean operations. In this particular case, I'll take an intersection with a circle and a plane so that it has a nice round perimeter and also a flat cutoff at the bottom. I think that's about the right size, and we can change it later. But essentially what I'm doing now is saying that my first bit of three-dimensional data is equal to that, and my second bit of three-dimensional data is equal to that. And it is actually 2D, but we can, the math doesn't care. It projects into 3D just fine. And here's where the first of our Boolean operations will come in. It's called an intersection. And essentially, in math terms, all that is the minimum between our first bit of three-dimensional data and our second bit of three-dimensional data. And you see that cut it off nicely. Next thing we'll want to do is take the base plane, and that is essentially just defining a region as z being greater than a certain value. So once again, we'll turn that into our implicit inequality here. 0 is less than, let's go with -3 minus z. And that's pointing in the wrong direction because once again, the minimum is an intersection. If it was maximum, it would be a union, and in order to do a cut, you have to do certain things to the signs of each operation. But as this is a basic tutorial, I'll only do the minimum required in terms of math. So all right, and just like that, we have our solid. Now, it does have a jagged edge. There's not much we can honestly do about that at the moment without going into fillets. And that's an advanced course that I'll be saving for later. But a few things we can do is, for one, that's a little bit thinner than I would prefer, so maybe knock that down to 3.5. That's looking much nicer. Now we will want to set our axis limits, because one downside to Desmos is that you cannot set the resolution. And if you chop the graph into multiple segments, it simply doesn't work. Alright, I think those axes pretty fully encapsulate our model. Not quite satisfied about that edge, but once again, we'll save that for a later video. Now all I have to do is go into the GitHub bookmarklet that I mentioned earlier. We can copy that link and add that to our bookmarks, which I have already done, and is very browser dependent, so I'll let you figure that one out. It's essentially the URL text has to be equal to that link that I have listed. Let me just take this text and format it with Word or app. And here is all the code. I mentioned that I plugged this into ChatGPT, and from how it explained it, it seems very safe, as a matter of fact. A bug might crash your computer, but that seems unlikely given just how simple the code is. Now all I do is run that bookmark, and we can wait a little bit. Sometimes upwards of 30 seconds to a minute, and it will appear in our downloads folder. While we're waiting for that to happen, I'll go into why I chose to use Firefox instead of other browsers like Google or Opera or Edge. Now, Firefox, from my experience anyway, has been able to deal with a whole heck of a lot more information stored locally on the computer than the other browsers have. I'm not sure if this is an actual feature or if it's just my computer that happens to like Firefox better. But do some testing. If it doesn't work, switch browsers, and then we will have our graph. Alright, it seems to have gone through. So just go into our downloads folder, double click on that because Meshmixer is my default my default OBJ opener. And you see that it doesn't look anything like what we just modeled. This is why I recommend Meshmixer, because the software does tend to add a bounding box to the model that you created. Just select those triangles to get rid of them. Make sure we don't get rid of anything we don't want to get rid of. Alright, now you see all those blues and reds across the surface of our part. If we wanted to actually do anything other than print this mesh, those would be a deal breaker, unfortunately. We can fix a few of them. For instance, in the edit menu, we can close the cracks, and you see that got rid of a lot of the blue edges. The blue edges are just locations where an edge is duplicated. But the red areas did not get fixed. Now you might think that you can go into the Analyze Inspector and then just hit Auto Repair All, maybe with a flat fill. But unfortunately, that just completely ruins your mesh. So we take this file, we export it back to the original file. And you can see that I've been doing this a lot. And we don't care that it's non-manifold. Hit the X button, don't save. Now we can open up Cura and slice this graph. Give it a second to load. Drag it over, and you'll see it's very tiny. And that is for a few different reasons. The main one being that the default units as exported from Desmos into the OBJ are in millimeters. And you'll notice that our circle had a radius of 1. So we just scale this up until it looks good, maybe 1000%. Drop it up to the build platform, slice it. It does give us these model errors, but it's smarter than it thinks it is, as you can see here. Once again, there's a jagged edge. We can fix that later in the next episode. You select the filament and the quality that you want, save it to your disk, and print it out, and that is that. Alright, so we've gone from an equation that we found on the internet that we thought would look pretty. We plugged it into Desmos, we exported it as an OBJ, cleaned that OBJ up in Meshmixer, and sliced it and printed it, and now we have it in front of us. You'll notice that it does not, in fact, have a jagged edge. That's because I fixed it in a process I'll show you in the next episode. But I think that looks pretty nice. A good paperweight to stick on the desk at work. Have an excellent day. This is Kevin signing off.